Thank you for having me, and welcome to my talk today. I'm going to introduce you to some of the physics of baseball. A little background about this talk. It really comes from a course that I taught this semester for the first time at VCU, based off a hobby that I've had for a long time, as many of us have had. Right, a lot of us play baseball, softball. It's a great sport, and it's a great summertime sport. And I guess with July coming up tomorrow and everything, it's like you're saying, it's a good time to talk baseball. Not sure how many people have been able to count the games. On this slide here, this is actually my introduction slide to my course. So kind of plugging my course a little in case any of you know anyone who might be interested in taking it. Things that we do cover, topics like running, throwing, fielding, kind of basics of motion. We'll talk about how the ball moves through the air, pitching and hitting. It's actually a 5-week course, so it's a quick lesson on how physics is involved in all of these things. And also you've got my email address there, which I will give to you at the end if you'd like to take that down. So, talking about baseball, the first thing I feel like we need to get familiar with is some of the dimensions. The baseball field itself, the infield, is a 90-foot square. The pitcher's mound is about 60, or is exactly 60 feet, 60 inches, or 60 and a half feet from the back of home plate to the pitcher's mound. The outfield, most Major League Baseball fields or I guess any new Major League Baseball field is supposed to have these dimensions, but they can always get, special permission from Major League Baseball if where they're trying to put it doesn't fit with other accommodations like big walls, like Green Monster and those kind of things. On the right, this is just a picture of the pitcher's mound. You can see the pitcher's plate. It's 6 inches by 24 inches. You've got this little platform here where the pitcher stands on, and they push off of that rubber. And the mound, it is called a mound because it's elevated about 10 inches. So 10 inches off the ground, put right in the middle of the infield. Other dimensions, we've got to think about the ball, right? The ball and the bat itself. The weight of a ball is about 5 ounces, 5 to 5 1/4 ounces. My son plays Little League, and his Little League ball is 5 ounces. I measured it the other day. 9 to 9 1/4 inches in circumference. Batter, or the bat, has to have a certain diameter. This is 2.61 inches maximum in diameter for a baseball bat to be legal. The maximum length for a bat in the major league is actually 42 inches. I don't know if anyone knows, or there might be some stories of someone who used to swing a 42-inch bat, but nobody swings 42-inch bats nowadays. They're too big, and one of the concepts we'll talk about today. Minimum weight is 32 ounces. Typically, Major League Baseball players swing around 32, 36 ounces, somewhere in there. That's kind of the standard. Same thing for length of the bats, usually around 34, 36 inches. And that has a lot to do with them just being able to swing a bat. And then on the right, we've got the strike zone, right? The famous or infamous strike zone that many of us have fought and battled throughout the years. The definition by the Major League Baseball Association is the hollow beneath the kneecap up to the midpoint, the midpoint of your back when you're in your batter's stance. Usually we say it's from shoulders to knees. And that's typically where it's an easy way to remember: shoulders to knees when you're in your batter's stance. So all these things are happening. All these dimensions are things that are in these small dimensions, in these small places. A lot of interesting things can happen. So the first part of this is I want to talk about the ball in the air. Right? So the ball in the air, we can't talk about ball moving through the air without talking about forces. So this is just a quick picture. You can see the ball is moving to the left with some velocity. We've got 3 forces that act on an object. Right? This is the projectile motion: weight, drag, and lift. Now, weight is actually, I'm not going to talk about that today. That's just mass times gravity, or the acceleration due to gravity. Again, we're going to talk about him in the next slide, but we can thank Newton for that. Drag and lift are the 2 forces that I wanted to focus on in this first section here. So drag and lift have pretty big impacts on how a ball moves. But I can't talk about forces without at least highlighting Newton's laws, right? Newton's 3 laws. The first law, the law of inertia, that's the one where a body at rest tends to stay at rest. A body in motion will stay in motion unless acted on by some outside force. So these objects will continue in a straight line unless some force acts on them. In our case here, we've got three forces that could act on them: weight, drag, and lift. The second law is probably his most famous law. It's the math one. That's how I refer to it with my students. It's the math one. F equals ma. This just describes the relation between acceleration and mass for a certain force. Or if there's a net force on an object, it will have mass. Or if there's a net force on an object that has mass, it will undergo some acceleration. And then the third law. Third law is the action-reaction force, where an object exerts a force on another object. That object has to exert an equal and opposite force on the first object. Now, these forces act on different things, even though they act together. Right? A force is really any interaction between objects. I've got an example on the bottom right here where there's an action force of a tire pushing on the road. Right? So if the action force in this case is a tire pushing on the road, you can see the tire. You can imagine the tire is pushing on the road to the left. The reaction, or the other force, according to Newton's third law, would be the road pushing on the tires to the right. And in fact, when we talk about this car moving, the car is moving to the right. So it's actually the force of the road pushing on the tires that kind of makes the car go. And that's how we illustrate this. But all three of these laws are going to come into play when we talk about everything here. So first, I want to show you this fun clip. If you can watch this for just a minute. A lot of Newton's laws going on in this one little clip. We have Ramirez, who's running with a certain speed. So we actually can even talk about momentum here, because the helmet is moving with momentum. You can see the helmet starting to fall off and roll down his body. And at the last second, you can see it, he kicks it up. And even though the camera's panning, so it's maybe difficult to tell, but he's actually kicking the helmet, looks pretty straight up. Right? So he's applying a vertical force to it. And the helmet lands on him. Right? So this is a clear demonstration of inertia. Right? The helmet's moving because it was attached to his body. So as it rolled off, it was still moving with him. And when he kicks it up in the air, the helmet is going to continue to move in that same direction. Right? So it's kind of a combination of the velocity of Ramirez running itself, the velocity that he's kicking the ball or the helmet up at. Those two things are going to, there's a velocity this way, and there's a velocity this way, which is actually going to produce a nice parabolic path where it lands right on him. That'd be pretty interesting if that actually landed right back on his head, but it's still, I think it's a really neat little clip that demonstrates Newton's law, definitely law of inertia. So drag force, right? Drag force is the first of the two I'm going to talk about. I have two set up here, low velocities and high velocities. In both cases, you can see that it's equal to the negative. The negative is just indicating that the force is in the opposite direction of the velocity. For low velocities, it's just kind of a general B term that we use for the drag coefficient. And you can see it's directly related to velocity. So drag and velocity are related. And we've all experienced this if you've ever put your hand out the window as you started to drive down the road. Right? As you increase velocity, we start to feel more drag on our hand. For higher velocities, it gets a little bit more complicated, because then we start taking into account, we have to take into account more of the shape and the geometry of the objects that are moving. So this is a general term here, this -1/2, the coefficient of the drag coefficient times rho. Rho is the air density. Right, the air density times the area. This is the cross-sectional area of whatever the object is, times the velocity squared. So when we get to higher velocities, the velocity plays more of a role with drag. So we can see that there's these two regions, and the regions really depends on the object, and it's kind of difficult to define where these things switch over. But this is typically how we see it in all these textbooks for these high velocities, especially for baseballs. And I underline air density because I'm not going to talk too much about it, but it's one thing to think about that it affects a ball in air. Air density, right? If we here, well, I'm actually not in Richmond right now, but if you're in Richmond, you're at sea level, right? Versus if you go up in the mountains in Colorado and play at Coors Field, you're in a less dense area. So the less dense the air, the further the ball is going to travel. So air density does play a role with drag and so does humidity. Actually, I left out humidity. Humidity is another important, because humidity actually affects the density of the air too. So more humid, less dense air, it can travel in more. Typically, balls can travel a little bit further. When I'm talking further, I'm talking 5-10 feet, not enormous distances, just a few feet. That could make a difference for a player hitting a home run versus not. But I've got this baseball played in this region here. An interesting thing that happens as you increase velocities for objects is something called the drag crisis. And this is a region where the coefficient, or the drag coefficient, actually decreases. So as you increase in speed, you get to a region where you get this drop off in the drag coefficient. So the drag coefficient, again, is this CD. On this graph, you can see drag coefficient versus this is RE. That's Reynolds number. Reynolds number is a way that when we're talking about fluids, because air is a fluid, when we're talking about objects moving through fluids, a lot of times you won't hear velocity, you'll hear Reynolds number. Reynolds number is a ratio of the inertial forces acting on over the viscous forces acting, like the viscosity of the fluids itself. So what you're seeing here, when you see Reynolds number, you can really kind of think velocity because it is directly related to the velocity. But there's this region here. This is the region where baseballs play, where baseball is played again. And that line is right around, again, where maybe to the left of the line would be some of the slower velocities, maybe like a knuckleball or even like little league pitches. The right side of that line is probably more, 90-mile-an-hour fastballs, 110-mile balls that are being hit, coming off of a bat. So this drop in drag coefficient is attributed to laminar flow becoming turbulent flow. And I've actually got a definition for that just coming up. But laminar flow versus turbulent flow. And turbulent flow has decreased drag. So that's what this is talking about. So this drag crisis has been observed in various balls, various objects. And again, you can see the smooth ball versus a rough ball. So viscosity, laminar flow, and turbulent flow, those words I just used on the last slide. Viscosity, if you're not familiar, has to do with the resistance of a liquid to flow. Think peanut butter versus water. You open up a jar of peanut butter, tip it upside down versus just a jar of water. There's a definite difference in how they flow. Laminar flow and turbulent flow. I've got this video here, which kind of illustrates laminar flow and turbulent flow. With laminar flow, you can see these smooth kind of vortices forming behind the ball that's on top. With turbulent flow, we're seeing just lots of like chaotic air moving all around. These are wind tunnel experiments. Now, I will point out that this has a tripwire on it, which means it's purposely there to kind of create some turbulence. But that's essentially the difference between laminar flow. Laminar flow is that smooth flow that we see around an object, where turbulent flow is where it kind of gets chaotic and comes off. In fact, I won't talk too much about it, but laminar flow, we talk about in this field, they talk about separation, how the wake of the ball, the wake is what's going on behind the ball, how that separates off of the ball, and where it separates off of the ball actually does help us determine what can happen to the ball and what kind of movement we can see with it. Laminar flow actually separates sooner than turbulent flow, meaning that turbulent flow sticks around the ball a little longer. This video on top is showing essentially viscosity and a property of fluids. You can see we have, it looks like a wall, and then we have this fluid moving to the right. And just paying attention to the fact that the fluid that's close to the wall is essentially staying there, right? So as objects move through the air that's near that object stays with it and moves along with it. So if the ball is just moving through the air, I've got a baseball here, just moving through the air is moving around it, the air is kind of staying on it where it is. That changes when we spin a ball. The air still stays there, but now the air is moving with it. But that's what this is trying to show, a property of fluids. Whether it's the object that's moving or if the air is moving past it, it's the same thing. It doesn't know the difference, but the air is staying close to the object. So that leads us to the next force, lift force. But with lift force, we're primarily talking about Bernoulli's principle or applications of Bernoulli's principle. You may have heard of Bernoulli's principle. This, simply stated, it's when the speed of a fluid increases, the pressure of the fluid is going to decrease. This is what's used in airplanes, right? They get them off the ground, that whole concept of lift. We can see these are streamlines kind of demonstrating air moving over a wing. So on the bottom here, we can see the air flow is pretty straight, not much deflection underneath it. But on top, you get this kind of bunching together of air of these streamlines. What that's demonstrating is that the air on top has to actually move faster than the air on the bottom to get over that wing. When you have the speed of that fluid is increasing, the pressure up there is decreasing. So essentially you get a low pressure up here and a higher pressure down below, and that generates a force, so that lift, right? That's what lift is. You may have observed this with your roof, hopefully not your roof, but you've probably seen it on TV. When we have strong winds, hurricane winds coming through like Richmond, airflow going over a roof can actually lift up the roof. And of course, this applies to a moving ball. Right? So I've got a ball here, just an example of a ball moving to the right with no spin and a ball with spin. If the ball is not spinning, typically we assume that the air flowing over the top is the same as the air flowing over the bottom. And if it's equal on top and bottom, then there's equal pressures and there's really no deflection. But you take that ball and spin it, now all of a sudden we can actually use Bernoulli's principle to describe this. The air on top would be moving faster, like in this picture on the right. The air up here, where B actually is, this air is moving faster than the air below, which would produce a force. And actually, I've got those. So this would also produce a force up, which is actually illustrated by this arrow kind of deflecting upwards. Now, there's one kind of misconception here that with this picture showing that the ball actually deflects up. In baseball, I'm going to say right now, it's impossible to get a baseball at normal baseball speeds, normal playing speeds to actually deflect upwards. Gravity wins out all the time, and gravity is going to make it follow that familiar parabolic path that we've seen. However, the spin and the Bernoulli principle could cause the ball to follow maybe a shorter path or a longer path, depending on how it's spinning. And this leads us to really what people talk about with balls and pitches being thrown is the Magnus Force. You may have heard of the Magnus Force before. This is a force that is created by on a ball, or really any object that's spinning through air. Force that is created by a spinning object that's moving through air. So in this picture on the right, you can see that the ball is moving with some velocity kind of to the right again, and it has some angular velocity. You can see it's spinning. And in fact, if you're familiar with physics and right-hand rules, you can actually use a right-hand rule. It's the cross product between the angular velocity and the velocity, and that tells you the direction of the force. In this picture, we could also see the other three forces. We can see gravity, we can see drag acting against it, and then in this case, the Magnus Force. The equations on the left are showing the relations that I took from Terry Bahill's book, The Science of Baseball. The first one, this top one, is showing the spin factor. And so we're showing that Magnus Force is related to spin. So the faster the object spins, the more you can produce a lift, or more Magnus effect that you can see. There's a lift coefficient, just like a drag coefficient, which is actually related to the spin. And so I'm calling the Magnus coefficient. And then if we actually want to determine the Magnus Force, this equation should look very familiar to the drag one. In fact, it's identical, except with a lift coefficient in there. And we could actually substitute all these in and show a relationship between spin and velocity, and how the Magnus Force is really dependent on those two things: how fast you can get that object to spin, plus how fast you can throw it. So for baseball, we're talking anywhere between 70 to 90 plus, or I should say 100 miles an hour for pitches being thrown if we want to take advantage of the Magnus Force. And then I have a few things here. The direction of the Magnus Force is always perpendicular to the velocity and the spin axis. That's the cross product. And typically the deflection tends towards the way the front of the ball is moving. So batters, if they see the ball, they can see the spin, they could actually somewhat predict where that ball might move to as it's coming towards them. Same thing goes for a fielder if they're trying to catch a ball. If they can see the spin of the ball, then they can actually use that to get a feel for it. So just as kind of a fun thing I do with my classes, I show them some pitches. This is the spin. This would be a ball moving towards you, asking them which direction would you see the Magnus Force on each of these pitches, and it's kind of based off the way the front of the ball is moving towards you, and these bluish arrows are also describing it. But a fastball Typically fastballs, pitchers put backspin on the ball. So you get a force that's kind of up. Curveball, they put front spin on it. So you get a force that's more kind of down, depending on the axis and depending on the arm angle that they release the ball. That also plays a role with how the ball is going to rotate. And again, slider, you can see that's moving this way, and the screwball will be moving down. These are kind of overall how you'd expect these pitches to deflect. Here, I took this from Barton Smith's work. This is showing the wake on a ball. On top, you're looking at a movie of the wake on a ball that's not spinning. And I just really wanted to point out that first off, there's blue and red. If you can see that, the red is just showing counterclockwise motion. The blue is showing clockwise motion. And then you can see a vortex and some things spinning here. But if we take this picture and look at it down here with no spin, this blue line and this red line are showing, again, the wake where the air is moving around, where it's leaving the ball. With no spin, we can see that they leave the ball at the same point. One thing some of you may be asking yourself is, with no spin, that's typically a knuckleball, right? Knuckleballs are balls that are thrown with no spin. Knuckleballs are something that people are still trying to figure out what's going on with them because they're just crazy motion. There's been a lot of work on them. There's actually been a couple documentaries on them too. But all purposes, what we're looking at here, if the ball is moving, we assume that the wake on the backside is leaving at the same point, and we're not getting any overall forces, any extra forces acting on it. If we spin this counterclockwise, we can see that on the top, it kind of shifts this wake down a little bit. And we can see this difference here. And actually, if we increase the spin even more, we can see more of a shift. So you can see the relationship between spin rate and where this wake leaves. So if this ball is moving to the left with counterclockwise, that's clockwise spin. I'm sorry about that. Clockwise spin. With clockwise spin moving to the left, this wake shifts down a little bit, which actually causes that force on it to go up. Other people have described this in terms of Newton's third law with action reaction. We talked about laminar flow, and as this ball is spinning around, the air is moving around it, it's staying with it, but eventually it separates and leaves. So as it leaves, there's a force on the air that's essentially, as the ball rotates around, there's a force being applied to the air. The air is also applying force back. That force coming back is slightly up. Here, so we actually do get a slight force up from there. So I'm giving you another description of why these balls can spin. There's a Newton's third law description, there's the Bernoulli's, and then there's the Magnus Force. Magnus Force is again an application of Bernoulli's principle. Oops. So I did want to just show just a few quick examples of Magnus effect in real life. I mean, these are just going to be, you're going to see some balls spinning, right? We can't see the ball from this angle, but the idea here is we're seeing curveballs, we're seeing balls just kind of moving all over the place. This is typically what we're seeing. We're seeing these are effects of the Magnus Force, and pitchers can take advantage of this. In fact, there's something else that I'm leaving off here with what pitchers can do, and it's pitchers. It's been in the news lately about modified balls, right? Like putting substances on balls. There's been some pitchers there who've been getting accused of it. By putting substances on the ball, if you can scuff up the ball, you can actually produce a deflection, which is not related to the Magnus Force. You can also vary the amount of spin that you put on the ball. So if we talk about spin in the Magnus Force, you can see all I'm showing you right now is a basketball being dropped off of a dam. I believe this is in New Zealand, and with no spin. So not much happening. You see the ball kind of moves around, maybe knuckle ball a little bit. If I show you the next one, which has some backspin on it, here, put some backspin on it. Notice it's much more stable and how it deflects and bends right away. And you can actually see the way he's spinning it. You could use the right-hand rule and figure out the direction. We can obviously see the direction of the Magnus Force is away from the dam. And I like this clip because it's just really neat to show. And I've got them side by side here. So you can see, the effect of spin on a moving object. This is much more dramatic than in a baseball, much greater distance and much large piece. We can really see the effect of the Magnus Force. So I thought that was fun. Hitting the ball. Next section is about hitting. With hitting, we can't talk about hitting without talking about momentum and impulse. Momentum, you can think of it as inertia in motion. Inertia is a property of mass. That mass moving is its momentum. Balls have momentum, the bats have momentum, even the people have momentum. So there's a lot of momentum demonstrated here. And we know that the greater the force and the longer the time of impact, we can have a greater change in velocity, which means a greater change in momentum. That's the concept called impulse. So you might hear a lot about impulse when we're talking about the actual collision between a bat and a ball. So I've got my little demonstration of this collision between a bat and a ball. Well, you can see this is my bat. The longer you can get those two things to interact, the more change in momentum you can impart on that ball. Again, the faster the ball can go. And the impulse is defined as, again, force times time. So I've got a question, how does this apply to the batter? What does the batter need to do to get the greatest change of momentum? The batter, if you're looking at him right there, we can see he has to start his swing early, number one. He has to get that bat off his shoulder and start moving. It's actually not even on his shoulder. He's got good form. But he's got to get that bat to accelerate. So he has to apply a force to it. That force is exerted over some time. He has to do impulse. There's a change of momentum. The ball itself is going from the left. Initially, it's going to the left, and it's after the impact, it's going to the right. So that's a change in velocity. So the batter is all about momentum, and actually conservation momentum, which is on the next slide. So the batter, what does the batter need to get the greatest change of momentum? He needs the greatest force and he needs the greatest time. So the longest time that he can, put this bat on the ball, which is why you hear coaches always say follow through, right? Follow through to try to make sure you can get as much time out. We're talking fractions of a second for a bat ball collision, but every second counts. And of course, we can't talk about conservation momentum. Here we've got collision at home plate. Conservation momentum is just the momentum before a collision has to equal the momentum after the collision, or I should say the net momentum before and after have to be equal, which means both objects will have momentum before and they'll have momentum after the collision. And typically we describe them as elastic, inelastic, or perfectly inelastic. In baseball, they're all inelastic. And what that means is energy is not conserved. There's always losses of energy with collisions. And here's just some close-ups of some collisions here that you can see a bunt. And we can observe the bat recoiling. So you see the ball coming in. We can see the bat go back. We have momentum of the ball and the bat beforehand, and the momentum of the ball and the bat afterwards. And here's a swing. And a nice swing, hitting the ball right on the sweet spot. And you can observe a little bit of some slowing down in this clip. The bat does slow down right after the collision a little bit. And again, that's all demonstrating conservation of momentum. So when a bat and a ball hit, when there's this bat ball collision, there's actually been some research looking at what happens to the ball after it collides. So this video on the left, you can see the ball is coming in with spinning clockwise, and when it hits off the surface, it spins counterclockwise. So we see this reverse and spin. This picture on the top right is just showing a bat ball collision. Typically, if you're hitting the ball towards the top half of the bat, that ball is going to go up into the air. If you're hitting it towards the bottom, it's going to go down towards the ground. And that's what this is showing. So here is some other videos that were taken by Alan Nathan from the University of Illinois. I got a lot of this information from. We can see the balls coming in and they're colliding, and there's backspin on the ball after that first collision. Here you're just seeing it hit. You're seeing some spin on the ball coming in, and you're seeing after it collides, it's leaving the bat with backspin. Same thing goes here. All these collisions where we're hitting the top half of the bat, no matter what the spin of the ball is coming in, we're getting backspin afterwards. That's what all these are showing. And then I think there's one here where we're hitting below, and you can see when it's hit below the bat, it's top spin. So this actually is important for batters, because if you are putting backspin on the ball, when you hit the ball, that's going to apply a Magnus force up, which will allow the ball to travel further. If you are hitting on the bottom half of the bat, you're putting topspin, which means it'll dive into the ground more, which also has an impact because if you put a lot of topspin on it, when it hits the ground, it could shoot off in a certain direction. So those are all things that fielders and batters need to think about. As I mentioned, these collisions in baseball are inelastic, which means there's a loss of energy. And I think in this video here, or this little clip, you can see very clearly a loss of energy. You can see the ball deforming. This ball was shot at a stationary bat. I took this from an actual show called Time Warp Baseball, or Time Warp, and then they were featuring baseball. The bat is actually stationary, it's just hanging there. I don't know if you can see my little bat. And the ball is coming in. I believe the ball was coming in around 140 miles an hour. And that would illustrate like a 90 mile an hour pitch with a 50 mile an hour swing. That's what they were trying to show. So these deformations that you see here do happen in an actual baseball. We don't think of that because when I feel this baseball, the baseball is pretty hard. But when we talk about that, we talk about coefficient of restitution. Now, the coefficient of restitution is, again, at its simplest, it's a speed after a collision compared to the speed before the collision, right? Or the ratio of the speed after, speed before. I know I've done little activities with this where I drop a ball, you drop a ball from a certain height, you measure how high it bounces off, and you can kind of get a quick understanding of the coefficient of restitution for various objects. A long time ago, I taught high school, and that's one of the things that we did. We froze a ball just to kind of see what would happen. On the right here is a much more complicated coefficient of restitution that actually takes into account the velocity of the ball, the velocity of the ball, the velocity of the bat, the distance. This is from the center of mass to the impact point of the ball, and the angular velocity of the bat before and after. So the angular velocity, we haven't really talked about that, but the angular velocity has to do with, hopefully you can see my little mini bat here, the little mini bat, the angular velocity, the bat is moving with some rotation. So it does have angular velocity. And actually, not mentioned here, it also rotates. People will roll their hands. So there's a lot of, angular velocities that are occurring here. But this is at its simplest. And for Major League Baseball, the coefficient of restitution for a bouncing ball has to fall somewhere between 0.51 and 0.58. And they determine this bouncing essentially shooting a baseball at 58 miles per hour off a wall that's made of ash, backed by concrete, because ash is used for bats. And then they measure those, and all the balls that that fit that requirement are good for Major League Baseball. And the last bit here is swinging the bat. So swinging the bat. Before we talk about swinging the bat, though, I want to do a quick calculation. Just basic average velocity is distance over time, and with an average distance from pitcher's release point. We said the mound was 60 feet 6 inches, but when the pitcher actually releases the ball, they're usually almost 10 feet closer, about 6 feet closer. So they're usually on average throwing from really about 54 and a half feet. And so if we use that as our distance and we use a 90 mile an hour fastball, kind of an average fastball, that gives us 0.4 seconds or 413 milliseconds to swing the bat. So for a major league pitcher or major league batter who's up there, they have less than half a second for a 90 mile an hour fastball to swing the bat and actually make contact. And just kind of a comparison, the average blink is about 150 milliseconds. So if a batter blinks during a pitch, they've missed a third of the path of the ball as it's moving through. So this kind of illustrates the importance of swinging and why you see batters, why we see a lot of batters strike out, number one, and why batters sometimes have to start their swing early. But we're talking fractions of a second to actually make a decision on whether or not they want to swing. And so for a pitch, I've got here any movement that could be impacted by that Magnus Force usually isn't seen until the last half, maybe third of the path of the ball to the plate, because this ball is coming right at the batter. And that's what I'm showing here. This is, I guess a local Virginia boy, Justin Verlander. You're seeing 4 pitches, all with all different types of pitches. And I like this because the overlay, you can see his motion is identical, almost identical. Where his arm slot is, where everything's coming from, it's all the same. The only thing he's differing is how he grips the ball or where he puts pressure on the ball. So we can see that, as the batter, if we think about this from the perspective of the batter, who has 0.4 seconds to decide if he wants to swing or actually swing, decide and actually go through with the motion of swinging the ball or the bat, it's very difficult. And a lot of the movement occurs late in the pitch. So these 4 pitches all look the same for a while. The only clues that the batter can use are spin. So a lot of work with pitchers, modern day pitchers, is even kind of hiding that spin. How do they hide the spin from the batter to get movement still and show these things? So that's a lot of interesting parts there. But if we're talking about swinging, we really can't talk about swinging without rotations. And when we talk about rotations, we always throw in torque. So think about how you open a door, how you open faucets. If you're familiar with torque, torque is what we call a turning force. I use the word force because it is the rotational analog to force in linear motion. Like a force equals ma, or F equals ma. A net force can cause a linear acceleration. A net torque can cause a rotational acceleration. So again, concept similar. We need torque. We need a force applied to a bat in order to get to rotate. And this is actually true even to get the ball to spin, but I'm focusing on kind of hitting. So when you take a bat and actually swing it, you probably all experienced picking up a short bat and a light bat. Right? Again, I only have short bats here, but if I were to swing this little bat versus a long bat, I'm going to feel a difference. Right? And this is what we refer to as swing weight. So batters feel swing weight. And I'm kind of comparing swing weight versus actual weight. The actual weight of a baseball bat might be about 2 pounds. But how that weight is distributed in that bat determines the swing weight. So if we were to move the center of mass of a bat up a little bit and get it further away from the pivot point, and the pivot point is down here, right? This is the pivot point, typically where our hands would be. And that's actually up to some discussion too. But let's say at the end of the bat is where the pivot point is. We move the center of mass from there to there. How does that change how the swing actually feels? And again, we all know that if we move the center of mass, or if we go from a small bat to a lighter bat, or if we, you may have heard the coach tell the batter to choke up. I know my son, who's in Little League, he naturally chokes up because he likes the way how much easier it is for him to swing the bat. But a lot of kids, we tell them to choke up because choking up kind of cuts down the lever arm that's necessary to that's in the torque equation, and it cuts down the next concept here, which we'll talk about, which is moment of inertia. So this leads us to moment of inertia. And moment of inertia is the rotational analog to mass. So something that's more massive is going to require a larger force to get to a certain acceleration. And that's true for rotations. So something that has a larger moment of inertia just means that the mass is distributed in a way that makes it harder to rotate with a certain torque, or harder to get to a certain acceleration. So the equation for moment of inertia is here. It's this mass times the distance from the rotation point, from the pivot point to where the mass is, squared. And we just sum up all these different points, no matter how many we have. So the first 2 pictures are just 1 mass and 3 masses to kind of give you an idea. But it applies to everything, or even a distribution of masses like a baseball bat. So again, moment of inertia is based off what mass you have and how that mass is distributed. If all the mass is at the end versus if it's evenly distributed throughout, it will have a different feel to it. And batters have to think about these things. That's why we don't see batters with 42-inch bats. That's why they're swinging 36-inch bats, because that 42-inch bat has more mass further out. It's harder for them to swing. And if they only have 0.4 seconds to actually decide to swing and swing, it makes sense for them not to use the heavier bat. They would rather err on the side of a lighter bat, where they might not get as much change momentum out of it, because that heavier bat will allow the ball, when it's made when you make contact, to travel further. But as a hitter, you want to make contact. So you want to use a bat that you can swing and get your bat on the ball. Now, making contact, when we talk about making contact, you probably heard of sweet spot. Batters want to hit the ball at the sweet spot. If we think about, Verlander's pitches, those 4 pitches, you want to hit the ball at sweet spot. So you see a ball coming in, you kind of almost have to guess where the ball is going to end up based off where you see the swing, where you see the spin of the ball. So you put your bat there. A lot of times, if that movement doesn't occur until late in the pitch, the batter doesn't have time to adjust for that, and the ball will move slightly, and they won't hit at the sweet spot. And this is where we see, if you've ever swung a bat and not hit it on the sweet spot, you know what I'm talking about. If you ever played in cold weather, you know what I'm talking about. You get that sting, that vibration in your hands. Or in the major leagues, they actually get a lot of broken bats. So the wooden bat can break. Mariano Rivera was famous for this. He was famous for having pitches that the cut fastball that the last second just appeared to move. So the batter was swinging where they thought it was going to be, but it moved at the last second inside on them, and they would break a lot of bats. So I've got a busy slide here. I apologize, but where the definition of where the sweet spot is up to some debate. There's a lot of words here. I usually focus on these. I'm going to focus on the center of percussion and then this node of the fundamental vibrational modes. These are two interesting ones to talk about. So the center of percussion definition really relies on this concept of a pendulum. So you've got your bat with a pivot point. The center of oscillation, if I throw that word out for just a second, the center of oscillation is the length of a simple pendulum, right? Simple pendulum is just a mass with a string that has the same total mass and period as the actual physical object. So you would find the center of oscillation for a bat from some pivot point. You can see there in that picture on the top left. The property about this location is if there's a horizontal force applied to the center of oscillation, no reaction force is felt, and we call this the center of percussion. So these pictures on the right are showing, let's say we have this object, this first object here, and we apply a force at the center of gravity. Right? This is a uniformly distributed mass, so the center of gravity should be right in the middle. So we're not even looking at bats here. If I apply a force, I'll get some velocity, I'll get some translation movement to the right. If I apply a force down here, I'll get some rotation about this center point. And that's, if I'm holding a bat and I hit it right in the middle, the whole bat's going to move. If I'm holding by the center of mass and I hit down here, the bat's going to rotate. That's what this is trying to show. So we get rotational motion depending on where the bat or where this object is struck. So now we pin the end of it. And we apply a force down low, like well below the center of gravity. And that center of gravity, when we're below the center of gravity, we're going to get this type of rotation, which means the handle is going to feel a force to the left. So if you were holding that, you would feel a force pushing on your hand. If we struck the bat or struck this object closer to the center of gravity, that behaves like this picture on the left. When we strike it closer to the center of gravity, we get movement, just like here, we get this translational movement, and you would feel that in your hands going to the right. However, if you struck it right at the center of percussion, what you would notice is nothing. You would feel no force here. And that's one of the definitions of the sweet spot. And we've all felt that. If I were to hold this bat up and just take a ball and kind of hit you, I don't think you could hear this through the computer, but if I were just to kind of knock the bat, there's a point here where all of a sudden I don't hear any ringing. And that's the center of percussion or center of oscillation for that object. And the second definition that I want to use to describe is harmonics and standing waves. So here, just if you're not familiar with them, waves, I've got a picture of a wave. A standing wave is a wave that appears to stay in the same place. Waves have reflections. So if I send a pulse down, think of a jump rope. If I were to send a jump rope pulse down, if I had one end fixed, I could actually get that rope to produce that pattern that's on the right. And when that happens, there's what's called constructive and destructive interference in this wave. The destructive interference are those nodes where those points appear not to move, and then the rope or whatever it is just appears to oscillate up and down. This happens in all objects. Objects have a natural frequency when they're struck. On the bottom right, that's showing frequencies for a guitar string. You can see the first harmonic, second harmonic, and the third harmonic just showing these standing waves that can be produced. Well, all objects have some kind of a natural frequency. When you strike a bat, the bat will vibrate. And that's what this part is. So with bats, we're going to look at really the first and second harmonics, even though the third and fourth are showing here. Typically with bats and bat ball collisions, most of the time we're talking just about the first and second bending modes. So here I've got an animation on the left that's showing the first. If we just focus on the first and second bending modes, here's a node. Here's one node and another node. And you can see that the bat is kind of oscillating up and down in between those 2 points. So that would be for this 34-inch bat that was used in this animation. Those would be those stationary points. And just to point out, these modes are vibrations are exaggerated quite a bit. With that first mode still identified here, the second mode moves out here a little bit. And so these are node, I keep saying mode, but node or vibrational modes. These nodes are stationary. And notice at the handle, this is where the handle is, this is where you'd be holding the bat. Again, these are exaggerated, but if these are nodes, these two positions here and here are areas where the bat would not move much. So the second definition that I talk about is this one, where the sweet spot, the sweet zone is identified as the area between those two nodes. Just another definition. The reason, again, we were getting minimal energy losses at this point. We can see that because of the vibrations in the bat themselves. All right. So just some little videos of a bat. This is a softball bat being hit at the sweet spot. You can see a little bit of slowing down, but we overall, we don't see much happening. This is what we typically see with a bat. If we hit the ball at the end of the bat here, you can see that vibration of the bat, the actual bending of the bat. And you can see that the hand on top, right, comes off when he hits. You can see the hand pops off. This is that sting. So if you hit at the end of the bat, you're familiar with the sting. And then the last one is on the inside. And here you can see even more kind of a violent kick away. The thumb is being kicked off the hand pretty violently at that point. So those 3 points hit at the sweet spot. You can see very, very minimal vibration, right? That minimal vibration corresponds to a minimal loss of energy. But if you're off that sweet spot and you get vibrations in the bat, their energy has to go into that. So there's some more energy loss in those last two types of hits. And if we take all this together, the swing, you can see the swing on this picture I have here. There's rotational motion. We actually have some translational motion also. We have the bat making this swoop. We have the ball coming in from over here. We have a little bit of translational motion. It's not all that well easy to see. We kind of follow it with the bat here along the handle. Right? There's some translational motion, the bat itself. All of this the batter has to do in 0.4 seconds. Make this decision, make contact, identify the pitch, which is again why batting averages are never very high. So physics can help us figure out the amount of force necessary to get the bat to a point. This is in a certain amount of time, but ultimately it's up to biomechanics and genetics to determine whether or not you're a good hitter or not a good hitter. That's beyond what physics is. So yeah, I'd like to give special thanks to Robert Adair, Barton Smith, Alan Nathan, Terry Bale, Rod Cross. These are Daniel Russell. These are all the people that all the information that I have from here is research that they have done for years. A lot of interesting, lots of new things going on with many of these, especially I'm following Barton Smith's work. Yeah. So thank you. Thank you for having me. If you have any questions, I'm happy to take them now. If you want to email me, we can talk about this. This is again a hobby of mine, or hopefully a new hobby of mine. So I'd be happy to continue the talk whenever. So thank you.
All right, thanks, Dr. Woodward. So we do have a couple questions here in the chat. So when we're talking about the turbulence of the ball in motion, how do the stitches and the material the stitches are made out of, how can that affect the travel of the ball?
That's a good question. I mean, the stitches obviously have an impact on the ball. And I can't even say that the stitches play a role with knuckleballs because I've made smooth balls knuckle before too. They move around. With turbulent flow, we're not sure about what role the stitches are because there's been some research done with high stitches versus low stitches, like on like professional balls. I think are smoother than college balls, or definitely smoother than little league balls. But yet we're still seeing these effects. So the stitches definitely do play a role with how the air flows, but because I guess if we take, for example, like a four-seam fastball, right? A four-seam fastball will be coming at you like this. The stitches on the top will be any impact or any influence that the stitches on the top would have on the airflow would be countered by the stitches on the bottom. right? So that flow over the top and bottom, because of how the baseball is, a lot of them will cancel out, is what I'm trying to say. A lot of the effect of the stitches end up canceling out. Now, there is a lot of work done with cricket balls. I don't know, I'm not a cricket ball, I should say I'm not a cricket ball fan, but I don't follow it. With cricket balls, they have just one seam down the middle. And so that one seam down the middle, they can actually take advantage of that and essentially have, it's hard to show with a baseball, but essentially have a smooth area on one side and then the stitches on the other side. And one of the interesting things that Barton Smith, which is why I highlighted him, is talking about is those seam shifted weights. So, they're looking at how the air moving over the seams versus another side can influence a ball. What the problem is, I really can't answer the question much more than that because I don't know. There's a lot there. They have been able to demonstrate that if you can get a scuff on one side of the ball, which could act like a seam, if you can get a scuff on one side of the ball, you can actually get that ball to deflect if you can keep that on one side the whole time. So if I scuffed up this side, as the ball will be moving towards you, it actually deflect away from the scuff. And the best explanation for that is that, yes, as the airflow is coming over this, you're getting a turbulent flow. On the other side, you're getting laminar flow. Right? The laminar flow on this side separates sooner than the turbulent flow on this side. So in other words, you have higher pressure, more air on this side longer than on this side, which would cause the ball to deflect. Now, the interesting thing is that, one of the first guy that I mentioned, Robert Adair, who's one of the early pioneers in physics of baseball, actually stated in his book that it actually goes the other way. So it's very interesting. He said that the scuff on this side would actually cause the ball to move to that side because he was applying Bernoulli's principle, where the air would have to move faster on one side than the other. But what they saw with some testing, and what Barton Smith saw with some testing, is that the scuff on this side actually caused it to deflect. And after looking at it, the best understanding we have right now would be the turbulent flow on this side, smooth flow on this side, causing higher pressure on the turbulent side, lower pressure on the laminar side, and causing it to deflect. So I guess that kind of answers the question with seams. It's just
okay.
Yeah, it's very difficult.
So can you talk about how much time a batter has to adjust to movement of the ball?
Yes. If we're talking, if we'll use that example of 400 milliseconds. Typically, they have about half that to really, during that 400 milliseconds, they have to make the decision whether or not they're going to swing. And that's based off of the hand release of the pitch and what they see happening right away. So a lot of times you see them coming in to start their swing. And then the overall time to make a decision, we're talking 100 milliseconds, somewhere in there, 100, 150 milliseconds to actually decide to swing, because then they have to get the bat. Now this is more anatomy, physiology type question, getting the bat there and how much time they need. But all of their decision making has to be made in that 400 milliseconds.
All right. So it looks like we're just about out of time for today. So thank you all for joining us today. And thank you to Dr. Patrick Woodworth for helping us discover more about our world. Please join us next week on Wednesday, July 7th at noon for Student Mental Health and Wellness, Returning to College Post-Pandemic, presented by Leah Stone, mental health counselor at Southern University and A&M College. You can register for next week's talk at smv.org. Each talk is free to attend and is open to the first 300 registrants. Thank you again for joining us today. Until next week, stay safe and stay curious. Thank you all for joining us.